I don't like you guys. Alright, fine, I'll sit.
What is? No, I don't know.
Alright.
Allison Johnson and Alyssa Nelson, please come to the office.
I don't think it's like ours. So I go inside, and it's like one of those campers that's like this big, but the pulled out. Oh yeah. And so I knock on the door, and he comes, he opens it. I heard her talking about this. I'm like, hey Mason. He's like, I'm like, sleep good? He's like, I've been sleeping since like last night. I got there. Sorry. And I'm like, what you been doing? And he's like, so he's like, come in. And I'm like, so I walk into his camp.
Alright, hey, welcome back. Okay. Alright, hey, welcome back. Okay, remember, if you were gone Tuesday last week, last week we got assignment, not that one. I haven't even wrote it up there yet. We got the page 312. You need graph paper for that. So make sure that if you have not already picked that up, I'll put it up here on the board. I forgot to even write it there on Tuesday. I'll put that up there. That is due this Wednesday. Today, I want to do a quick review of what we learned, okay, on Tuesday and Monday last week. To make sure that you're kind of on the same page, you know those 5 steps you have to do for your homework. Does that make sense? Okay, let's do that. Once we're through that, I want to go through at least one problem, where I introduced for the first time, how do we know where those peaks and valleys are when we're drawing? So that was one of the questions I had last week. Like, Ward, how do you know how tall to draw those? Where are we going to go? I'm going to show you that process today. We're only going to do 1 or 2 of them. And I promise you I would show you that because it's something you've already learned in this class, but we have to put it all together now. Does that make sense? So it's pretty straightforward. It's kind of a nice little review day, get you back in the swing of things. So once we're done with 1 or 2 problems, if you feel comfortable, I'll let you kind of work in your assignment and I'll put it up there. Okay? All right. Graph paper if you need it. I have some up here, so if you need to grab some. You'll need graph paper for your notes today. I think you had some graph paper. You're going to want that out right now. Because we're going to try to go as exact as possible in this drawing.
Oh, Lord.
Pulls out like a box. He has like 2 other boxes on the end in there. He takes one and he shakes it a little bit. I'm like, you.
Okay. All right. Hey. Okay. So, hey, if you haven't already, here's our first example. This is gonna be my one, maybe my only example today. If we have time, if you want to go through another one, we will. But I want to give you some time where you can get back in the flow of things today. Get us kind of back into that school frame. All right. Let's talk about our 5 steps. Now, if you don't remember what those titles were called, leading coefficient test. You know, testing where the tails go. We had x-intercepts, y-intercepts. We'll talk about what the symmetry could look like, and if it is even symmetric, and then we'll talk about the turning point. Then at some point we need to discuss how do we know where the peaks and valleys are going to go. Now the y-intercept on this problem is ridiculous. It's way out there. It's one of those problems that just kind of made it up. It was just, I know the number was crazy, but I want to make it work out for the later stuff. Okay. Hopefully this works. I made it up earlier this morning and I'm pretty proud of it. Okay, here we go. All right, first step. Let's look at the end behavior, the tails, the leading coefficient test. What is my biggest term on this function? It's polynomial. X to the third. All right, so what the x to the third tells me a lot. Number 1, the 1 out front is a positive number, correct? So that means that this graph will be drawn normally. It'll be a normal looking graph. What I mean by normal, the tails will go where they're meant to go. It's not going to be the opposite type of graph. Okay? And so now, to know where the tails go, we have to look at the power. This is an odd number. So that means the tails, the end behavior on this one, the end behavior, the tails are going to go different directions. So one tail's going to go up, one tail's going to go down. That's what end behavior means on this one. That's why it's an odd graph for the end behavior. So where do the tails normally go?
One goes up to the right, one goes down to the left.
Exactly. Left and right. Does that make sense? That's a normal looking odd graph. Down, left, up, right. So we're getting back to the swimming things, right? All right, so now that we have that, the next thing we can check, now that we've done the leading coefficient test, that's all that test was, tells us where the tails go. Now I want to figure out x-intercepts. So this is where we're going to need to factor this thing apart and see what happens here. Okay, so I'm going to put that function over here. What do we have? We have x to the third plus 6x squared minus 15x minus 90. Okay. So, on the first one here. On the first, let's look at this. Now, obviously, we can't combine like terms here, so it's probably going to have to be a grouping method. There's 4 items going across, trying to factor this thing apart. So let's group the first two together. What should I take out of these two? 2x, right? X squared. We're going to take an x squared out. So if we take an x squared from this, there'll be an x left plus the 6. Make sense? Like factoring into x squared out of both of them. All right, now in the back, I'm going to probably take out a 15 and a negative sign. Because I know 15 goes into 90. I know that. So if we take out the negative 15 here, what's left in the back is the x, and then negative 90 divided by negative 15, because that's what I pulled out, is a positive 6. That's 90 divided by 15. Goes to 6. Okay, so does everyone see what I did? I pull up common factors for the parents. Grouping. Okay, now, do you notice that the red side here and the left and the green side here, they have something in common? X plus 6. We can take that out as well. So that's going to go way out back. I'm going to take the x plus 6 from both of them. Now, if I took the x plus 6 from both terms here and here, the x plus 6 is gone. What's left? X squared minus 6. X squared minus 6. That's what's left. That's factored. That's factored completely. We went as far as we can. This almost was a perfect square. Not quite. Almost. Okay. Questions, comments on how I just did that? How I factored like grouping? Okay, I know this is one of the hardest types of factoring, especially like when we're at Thanksgiving break. Okay, but now we need to figure out, where this thing could potentially hit the x-axis. So how I do that, figure out x-intercepts. Basically, what you do, take each of these and you set them equal to 0. So take this, set equal to 0, see where it's going to hit the x-axis. Is where would it hit 0 for the y space. So what would make this thing 0, you move the 15 across, positive 15, the square root to the other side, and that'd be plus or minus square root of 15, which is almost what? Where's the square root of 15 roughly? Almost 4. The square root of 16 is 4, so it's 3.9 something. So it's almost close. So it's positive 3.9, negative 3.9. It's positive 3.9, almost 4, negative 3.9, almost 4. There's 2. And again, when you take that square root, there's always 2. Right? It's positive or negative. Principal square root versus the opposite. Okay, did everyone see how I did that? What about the back parenthesis? What will make the back parenthesis 0? Yeah. Again, what will make this 0? You just move the 6 over to negative 6. That's the easiest way that I can remember how to do it. So negative 6 is, let's see, 4, 5, 6. All right. Now, from right now, can you tell me, is this thing going to be symmetrical? No. I know that. Look at the x-intercepts. They're not even balanced. There's 2 over here. There's only 1 over there. It is not perfectly symmetrical. So So I know that the symmetry test later will fail. We know that. But I'm going to... Okay. Questions in how I found the x-intercepts. I know that x squared minus 15 is tough. Like you have to set it equal to 0 and actually solve it.
Or if you want us, when you do this on like the test or whatever, do you want us to use x squared and 15 or like let's say it's x plus or minus root 15, you want us to get these x.
Oh, you just write plus or minus 15. Right. When you draw the picture, you have to put the dots roughly where they go. Okay, yeah. Don't give me the decimal. Okay, we go with x-intercepts now. Be factor, that's what we do for x-intercepts. Hopefully it's factorable. That's what we're praying for. Okay, y-intercept. So y-intercept, we have that little rule that we do. What's the rule for y-intercepts?
Plug 0 in.
Exactly. You plug zeros in for every x that we have. So that is 0, 0, 0, minus 90. Which is? Negative 90. It's way down there. I mean, it's gone. That thing is negative 90 down the road. That is way down here. I can't even fathom how far that is down. Okay, that's way down the road. Now, let's see. Now that we have my y-intercepts, we have my x-intercepts. Oh, we should probably look at the multiplicity. Is it bouncing off the x-intercepts? We know we're passing through that y-intercept at some point. We'll get back to that here in a second. All right. Is it going to bounce or pass through these? What do you think? Look at the powers on these. Pass. The parentheses are all ones. It's going to pass through every x-intercept. Odd numbers means passing through those. So I'm going to pass through this one, I'll pass through this one, and I'll pass through the last one. So if I can draw these tails where they're going and get a rough glimpse here. So the tail is going this way. I'm going to pass through this one, which is negative 6. Some point, we're going to do that here in a minute. It's going to turn around, pass through this one. It's going to, I'll just go way down here. Turn around, come back up, and then it's going to pass through this 3 point and keep going. Okay, does that make sense? It's going to do something like this. So obviously, we have some really crazy, like, turning points on this thing. You know, this one might be normal. It might be pretty reasonable, like where that's going to turn. That one's crazy. Like that point way down the road. So we'll figure that out later. Okay, questions, comments on how I did y-intercepts, how I did x-intercepts, or the leading coefficient test for the tail scale. That's what we did last week, correct? Obviously, this is a little bit bigger problem, but we're getting in. All right, symmetry test. We can already tell, like, I knew it was going to fail, but we're gonna do that test here anyway, just to check this. Okay, the turning point test. You take the original function, which it has to be written in expanded form. This is expanded form. So when every x is by itself and it's not factored apart, that's expanded form. You plug in a negative x into it. So I'm going to plug a negative x in here, plug a negative x in here, a negative x here, and the 90 doesn't have anything, so I don't do anything with it. Right? There's nothing to plug in. There's no variable on it. And what we're going to do is we're going to check, does this thing turn out to be the original thing we started with, or does it turn out to be the opposite of what we started with? Opposite meaning like every sign is flipped. Okay, the power of 3 here means the negative sign will stay, negative x cubed. Right here, the negative sign will cancel, making that positive. Right here, the negative sign will go to the outside, making that a positive 15x, and the 90 doesn't change. So is this the exact same thing we started with? No. Is it the exact opposite we started with? No. So that's why it's not symmetric. This thing is not symmetric. So for it to be symmetric, it had to be the exact same thing you started with, or it had to be the opposite, where that was negative, negative, positive, positive. There was no way to turn that. I could have told you right there. There's no way to turn that 90 because it didn't have to vary this one. Okay, so it's not symmetric. We can see that from the picture across the y-axis. Okay, turning point test. What's your biggest power? 3. Subtract 1 off of it. 2. This thing should turn directions twice. So as I go from left to right, it turns once, twice, and then it goes off forever. So the turning point test did pass. And the reason why it did pass is we hit every x-intercept we should have. Okay, so this is everything we did last week. You're looking at it. The only thing we didn't do was go one step further to figure out where are those peaks and valleys at. That's the thing I want to talk about today. Like, just intro it. Because it's something we have definitely discussed. I just never told you what we could do with it. Okay? Make sense? Okay, so this is why I wanted you to have this problem. So this is the part where you're going to definitely need your notebook. And I know this is definitely going to be a pain in the butt. Okay? I know this. That's why we're going to do about one of these today. So you can see this. Okay. So now, what you're about to see is how do I know where the peaks and valleys are? Like, where is this thing going to hit? Where is that thing going to hit? And what would the coordinate be for it? That's what we're going to look at. This is not for the faint of heart. Okay. Are we good so far? Okay, here we go. Let's walk through this. So here's my function. It's always good to have it back in expanding form when you do this too. You don't want to have it back. You need the rest of it. Okay. Now, how we're going to do this. This is something we have definitely done before. It was actually on our last test. Is that differential quotient thing that I had in the last test. I never really talked about it. It's basically what we did for differential quotient. We just used it for just substituting practice. How do you substitute things in? What would it be if you simplified it? That's what I showed in the last chapter. The last chapter had a lot of substitution stuff. Plug in a 3x into this problem. What would that turn out to be? And you plug in 3x everywhere and you simplified it. It only went so far. What the differential quotient did is it did this. Is it took your function, it plugged an x plus h into it. It subtracted the original function off, and it divided everything by h. If you can remember that formula we had in the last test. Here's the difference. What we're going to use it for. What I want is basically what we use this differential quotient for, other than just substitution. It was basically slope. That's what we used it for. Okay. It was for slope or instantaneous rate of change. Not an average slope, instant slope. That's different. It's different than just doing y minus y over x minus x. There's a difference here. I can find slope on any curve if you just tell me the coordinate. And that's what I want. I want to basically find the differential quotient. I want to find that formula for slope for this curve so that what I can do is eventually tell you, like, if I knew this coordinate, if I knew that coordinate perfectly, like the x number, I could plug in the x number and it will tell me the slope at that moment. Well, what should the slope be right here? It should be 0, which is awesome, because that's the one spot slope will be 0. The only spot. It's the only time it will be horizontal. Everywhere else it's tilted. And then down here, there'll be another one where slope is perfectly 0, where it's a horizontal line as it turns direction. That's what we're going to be looking at. Okay. So I'm gonna show you how to cheat this to use this differential quotient in your favor. Okay. Now to do this, we have to modify the differential quotient just a little bit. What I mean by modify it, we're going to make this a limit, and I want to explain this idea of what a limit is. Okay, a limit is like a hypothetical idea, right? Like, you know there's a speed limit to your car. Agreed? Like, how fast can your car go before? 118. Okay, some people know exact numbers, which is scary. Okay, all right. So, like, there's a limit, right? You know that there's going to be a peak. Well, what a limit does is it looks down the road and goes, okay, what will the absolute, like, maximum be or minimum be at this very moment? That's what a limit can do for us. And this is the mathematical term. You put LIM out for your function. And what I want is I want to know when h, this h number, will be as close to 0 as possible. So minimum. When h will be 0. Now you're probably wondering, why do you want that? Why do you want h to be 0? I don't want it to be 0. I want it to be as close as possible 0, like a limit, right? Because I want to know when will your slope be as close as possible to the real number. Because if I make the x numbers as close to 0 as possible, because that's what this h is. It's when you're bringing these x numbers from the bottom. This is what looks like slope, right? Y minus y, x minus x. I want to bring these numbers as close to as possible, like squeeze the x numbers together. So slope will be as exact as possible. That's what I'm doing here. That's what a limit does. I'm bringing my slope together so it's perfectly the exact slope that I need. Okay, so I'm going to do this differential quotient just like before, and we're just going to have this thing copied down in the front. So really, this is not affecting it. It's going to be the same work we did in the last chapter test. This will just follow us all the way down. So here we go. So limit h approaches 0. Okay, so this is the f of x, but we're going to plug in the x plus h into all the spots where there's x's. So I have the x plus h, x plus h to the power of 3, plus 6x plus h squared, minus 15x plus h, minus 9, right? So what I just did here is I took my function and plugged in x plus h into all the spots where there's x's. Does everyone see that? Then I have to subtract the original function off. I'm going to subtract the original function, which is x cubed plus 6x squared minus 15x minus 90, all in parentheses, and this is all over h. Now what I'm going to do is I'm going to simplify this pretty quick. I'm going to try to go as fast as I can to simplify this. Now, before I start simplifying, I need to understand what do these things mean. Like these things. There's 3. So I'm going to have to FOIL this x plus h into itself 3 times. Okay? Right here, I'm going to have to FOIL x plus h into itself twice, and then take it times 6. Then all the rest of the stuff is very easy. I can distribute negative 15. Back here, I can distribute the negative sign. In fact, I'm going to do that right now. Negative 15x, negative 15h, right? Distributing the negative 15. The negative 90 didn't change. Distributing the negative sign back here, that's negative x cubed, negative x, or negative 6x squared, positive 15x, positive 90. And this is all has this limit as I want h to get as close to 0 as possible. Okay, so does everyone see what I did there? Distribute the negative 15s, distribute the negative sign to the back. This is why we learn that process. There's like this ultimate thing that I wanted to show you. Okay, now I'm going to FOIL this all together, and you're about to see some crazy stuff because we go as fast as I can. So if you, now at this point, does everyone have that written down? Okay, once you get to here, you can stop writing until the end. Okay? That way I'll save you some time. Agreed? That way you can just kind of watch what I'm about to do. Because I'm betting on most of you know you can do this. It'll take you about 20 minutes to do. So I simplify. Okay? So once you get to that black part, just stop. I'll do the rest of it for you so you can write down what your final answer is. Okay? So you should know. You can put like dot, dot, dot until you get down to the bottom. So I'm going to FOIL those first 3 parentheses together. So I'm going to do that pretty quick here. H approaches 0. All right, so FOILing the first 2 parentheses, I have x squared plus 2xh's plus h squared. That's FOILing the first 2 together. Now what do I have? I have that 6 times the x squared plus 6h squared. So that's FOILing these 2 together, and then distributing the 6 over it. I just did it automatically, so you can see that. Negative 15x, negative 15h, minus 90. And then I have a minus x cubed. Can somebody keep reading that? I have a minus 6x squared. Okay. And this is all over h. And I'm not done yet. So I got to FOIL the first 2. That's why I said that. You can just watch. Okay, so now I need to FOIL these first 2 things together here. That is x cubed plus x squared h. Now 2x squared h, and then 2x h squared, and then h squared x, and h cubed. So that should be 3 times 2, there should be 6. 1, 2, 3, 4, 5, 6, 6 items. Then plus 6x squared plus 12xh plus 6h squared minus 15x minus 15h minus 90 minus x cubed minus 6x squared plus 15x plus 90 over h, which is the limit as h approaches 0. Okay, so now I can divide everything by h's, correct? Because there's an h on the bottom, I can combine like terms. So, and certain things cancel up here. Like, the certain things that cancel. X cubed is gone. The 90s are gone. The 15x's are gone. The 6x squared is gone. So, right now, I only have things with h's on them. Because that's what should happen if you do the differential equation correctly. So, I have the limit as h approaches 0. That's x squared h plus 2x squared h plus 2xh squared plus h squared x plus h to the third plus 12xh plus 6h squared minus 15h over h. Okay, questions on what I just did there? Okay. Alright, this is the next line you can write down. Now you can pick up your pencil. Alright. I'm going to divide everything by h's. So what happens when I divide everything by h's here? Certain h's go away, right? Yeah. So certain h's are going to go away. So here's where we're at. We're at limit as h approaches 0. We'll get to that here in a second. I'll explain that concept. But we're going to divide everything by h. So if this has an h, these h's are gone, that h is gone. This will go down to 1h, right? So this is x squared plus 2x squared. That has 1h left on it. This has 1h left on it. That has 2 h's. H is x, right? Then I have h squared. Here, that is a 12x. Right there, that is a 6h. And back here, a negative 15. Okay. Questions on that? Notice, no fraction anymore. Agreed? So I've divided everything by h, and I'm down to this limit idea. Okay, so does everyone have that written down? Did I do my math right, number 1?
Yep.
Okay.
Everything's perfect.
Okay, alright, good. Now, at this point, if you look at what the limit is, what is the limit telling my h is supposed to be approaching? 0. My h's are approaching 0. So if that's approaching 0, what happens to this? If this actually turns 0, what would happen here?
0.
Yeah, that's gone, right? It's plus 0. What would happen here?
0.
0, that's gone.
0.
0, that's gone. That's still there. This would turn out to be 0, that's gone. So what I'm left with, if all these h's are approaching 0, they're getting as small as possible, this is what I'm left with. X and then minus 15. That is what I'm left with. What this is the reduced function. The reduced function, all the way down. This is the function that represents slope for me. It's the slope of my curve. It's called the slope function, or what you're going to know as in calculus is the first derivative. It is the first derivative of a function. What that means, it's a big fancy word for saying it's your function's slope, the instantaneous rate of change. That's what this is standing for. Okay, now how they show that on like paper. This is Isaac Newton's own like notes and how he wrote it. He wrote it like this. F prime of x. That is not a 1. That is like an apostrophe. Okay, F prime of x, that's how they write it there, right? Prime. F prime of x is equal to x squared plus 2x squared plus 12x minus 15. Yeah. So, okay. So did everyone kind of follow with what I did with the different? We did that before. Not a big deal. But this is representing slope. How I'm going to use it for my purpose is how I'm going to show you how to multiply. Is that what your question was?
When will we ever do this in real life?
Calculus. It's an engineering problem. bucks. Big bucks.
I don't want to.
All right. Now, I know. Not for the faint hearted. I told you so. All right. Now, here's the idea.
Something else.
How this applies to my picture. Because I did say I want to show you how you find the peaks and valleys. How you find those points. Well, the idea is that if this is slope, what I need this to be is 0. If I can get this function, this slope formula, to equal 0, that will help me find this point right here. That's where the slope is 0. And the same with the one down there. If I can figure out where these spots are making slope as 0, I can tell you where those peaks and valleys are. In fact, it'll give me the coordinates for it. So that's what I'm going to do right now. I'm going to take my derivative formula over there, which is, what is that formula? I'm just going to read off what's in the box.
2x squared plus 12x.
Okay, so I added the x squares together. So we have 3x squared. All right, so this is my f prime of x. Adding the x squares together is 3x. All I need to do, if I want this thing to be equal to 0, like my slope to be 0, I could factor this thing apart if it's possible. If it's possible, like figure out a way to make this, to make the 12 on the inside, which it is, plus minus, and put the 15 here, the 3x here, 1x, and 1. Because this will make 3x squared, negative 3x, positive 15x, which will make the 12 in the middle, negative 15. And all I need to do is tell me, where does this thing equal 0? Yep. Negative 5. That is my x coordinate where I'll hit a peak or a valley. Where will this thing be equal to 0? 1, right? That's my other coordinate where I'm going to hit the valley, the biggest valley possible. So in fact, this thing should have curved, and after it came back to 90, it was actually going through here, and it was actually coming back here. So in fact, I drew this a little bit wrong. It was actually doing something more like this. Going through 90 first, and then hitting the valley and coming back up. So it was past 90 where we were seeing this valley. These are the spots. If I want to know like exactly where that is, like where that peak is actually going to hit, that's my coordinate. It's going to be negative 5, comma, some number. 1, 2, 3, 4, 5. This is where that peak will hit. And in fact, you can see it right there. 1 is where this peak is going to be. This is actually the valley. It's positive 1. And all I need to do, if I want to figure out that peak and valley, plug those numbers in. You take your function, and you actually plug in a negative 5 in here, like on the original function, and it spits out your number. If I plug a 1, it'll spit out my number, which is crazy. Like, you can actually do this. Now, the best part is, so you're probably going, God, we got to do one more step. Let the calculator do this part for you. Let the calculator do it. Because all I need to do is type in the calculator. What's negative 5 cubed plus 6 times the negative 5 squared minus 15 times the negative 5 minus 90, right? It'll do all the math, and you can enter, and it'll spit out the tallest point that we hit. And if I do it for the number 1, I plug in 1 cubed plus 6 times 1 squared minus 15 times 1 minus 90. It'll do all the work. In fact, I'm going to just use Wolfram Alpha to kind of show you the idea here. I want to show you that Wolfram Alpha can actually just, you can use it as a calculator. So, I'm going to take my function, my original function up here, and I'm going to plug it into Wolfram Alpha here. Alright, so we're going to take, let's put this up to the top. I'm going to take my original function, which is over here, and I'm just going to plug in the negative 5 and hit enter. It'll spit out my number. So parentheses, negative 5 cubed, plus 6 times the negative 5 squared, minus 15 times the negative 5 minus 90. result here, that when I actually typed in the -5 into all these spots, told me that my highest point was going to be 10. It'll hit 10 here. So this is -5 times 10. Isn't that awesome? I can do that. Now what I can do is I can go back up top here, and to figure out where the valley is, I'm just going to change all these -5s to be +1s. So in fact, I'm just going to go to the bar up here and change these to be +1s. Enter, it was a -98. It actually would do it before you can enter. So, -98, and this was a 10. Now to prove it, I'm going to graph this function for you. I'm going to actually prove that those are the actual peaks and valleys we hit. Because again, that's what the differential quotient is there for. Okay, so let's go back to my original function here, and let's graph this. So y equals x cubed 6x squared minus 15x minus 90. So let's zoom in here. It's getting really far away. It was trying to zoom out far enough that we can actually get a glimpse for where these are. So, and we can enlarge and we can go closer, row features. But all right, so we're hitting 98 here. We're hitting -98, I should say. So that's why they zoomed out to hundreds. This is 10. That's every mark that we're going up. We're going up by 20, 40, 60, 80. So it was about halfway. So it's 10. So it is proving like where my peaks and valleys are. Isn't that nuts? Like we can. The simple things that we've learned. Now I know a lot of you are like, oh, that isn't simple. It is just an easy process though. I mean that you're plugging in x plus h in your function, subtracting the original one off, and it gives you that hypothetical where we can actually hit the x-axis. And it gives us our peaks and valleys. Now you're looking at this going, God, you have to do all that. Yes. When I was in school, we had to do all of this. Now obviously, this is the first day you're seeing actual Calc 1 material. They teach you how to do this over an entire semester of Calc 1, like how to figure out these peaks and valleys and what they're used for. They never show you that until about the end, like why are we doing it? To find those peaks and valleys where the slope is. This is where potentially you hit a maximum profit or a minimum profit for a while. That's the idea. That's what we're doing. Now, how I did this, I reverse engineered this problem. I knew where the peaks and valleys were going to be in the beginning, and I went backwards to make it what the original problem was. That's what you can do. So if you're in a business class, a lot of you are like, when are we going to do this? If you're in a business, let's say you have some advanced math skills, so you're like a business major or minor, you do have to take a lot of calc. You can start with where your peaks and valleys are, like what money you have now versus where you want to end, and you can reverse engineer the problem to make sure that you can hit that in a timely manner. Like what you need to do. Oh, I need to make certain sales by then to make that type of money. Because that's what I did. I just started with these two coordinates, and I went from there. Okay, questions? How I did this? Okay, that is a lot. I know it is. That was throwing an extra step. You don't have to do that. I wanted to show you that. Because that does take actual calc. Okay. All right. Questions, comments on what we've done here today? Okay. I know I don't give you a lot of time. You do have an assignment that was due next week. Or actually, not next week. On Wednesday, I should say. On Wednesday. All right. So, this is the assignment that I gave you on Tuesday last week. Here it is. All right. It is page 312. Remember, you're doing numbers 15 through 18. Hey, on these 15 through 18, remember, you're just giving me what letter is matched. They give you the pictures, they give you the formula, you have to figure which one is which. 48 through 54, the evens. Those where you're going to have to do all the steps. And then 56 through 62, evens. these are already factored apart, so you already know your x intercepts. You have to go further to graph and all that. Remember, this is due Wednesday this week.
Wednesday?
Due Wednesday. Okay, who needs graph paper for this assignment? Anyone need it? Okay. There you go.
Student's name on your name and one of those small letters. Are you on there? Oh, Kyle Burris. Andrew Bryant.
Oh, yeah.
Nathaniel Burke.
$60.
The other brother's name is Nathaniel.
Yeah.
That's
Oh, okay, minus 60.
one shirt and Burke.
And all you have to do is you bottom ground zero, got them and then you set up the website and then people place orders on them and the only thing he has to do is ship them out to people. So he goes, he clicks on the order, he prints out something, puts it on an envelope, and then he has it set up to where it goes directly into his bank account. So he's already paid I think I might do that because honestly,
Hey, Jack.
like I would have never thought of ever doing that. And I'll see if I can find it. It's one specific person and stuff though.
Ward, I'm getting told.
Kathy, Anna Albrecht, please come to the office.
Oh, what's happening here?
Spencer Duriger, Stacy Hartman, Haley Harris, Anna Wellick, Nicole Upmeyer. You have something in the office?
Ohio State on lockdown. Where'd you get that sweater?
What?
Where'd you get that sweater?
Cold?
I love Kohl's.
Don't you go Black Friday now? I've seen like everyone.
I did. Soft.
I seeded everyone.
Can't say that.
Seeded isn't even a
Not
word.
even.
Okay, that actually is. Definitely not it. You shorts. Yes, I'm in shorts. Because I'm socks. Oh, I'm wearing the same socks.
I got a chore for you to do.
Sure. I'd practice go.
Okay.
Yeah. I do not. Nah, not today.
As soon as we got the people out of the second time. He's just like, oh my god.
Why do you always have to try to back?
Depends on what.
How many different colors I have? Some brown, some gray, some maroon, whatever this is.
No, I'm gonna do this.
I would have that red there for it. I can't wear jeans. No.
Why? Because of Poshmail.
What are you doing?
Never gonna do that.
Have you what house do you go for? What?
I don't even remember.
It'll be hard.
So when are you going to
It might just like in a couple months when email. Yeah. You'll have your roommate by then, you know?
Oh, we're
And then it'll be like for your what American for your top years learning. Just like for your house.
Or you can be like, you